Hey, everybody. So I've had a few good conversations with several of you over the last few days, including conversations about how difficult some of this material is, these sequences and series and all the convergence tests. Totally get it. This is a notoriously tricky section. There is a lot of stuff coming at us right now. So I wanted to take this moment to kind of summarize the beginning of what we've done and then point us to where it's going, because um, we're learning all this information about sequences and series and how to test for convergence. And then we're going to take a turn into, it turns out we can represent functions with infinite series, which sounds like a needlessly complicated thing to do, but it turns out it's not as complicated as we might think, and it's way more useful than it sounds. It turns out to be a really, really important part of math and science. And so we're about to take that turn where we go from just sequences and series of terms to ones that represent functions. So before we take that turn, I kind of want to take a little overview of what we've done, okay? So one of the first confusions is just keeping track of what is a sequence and what is a series. In common language, let me make this a little bit thicker. In common language, we often use these terms interchangeably, but they're two very distinct things in mathematics, right? So a sequence is just going to be a list of numbers, right? And we're exclusively, almost exclusively in this course dealing with infinite lists of numbers, right? And testing their convergence, right? So we'll use the term convergence when we talk about sequences and series, but we mean different things. When a sequence converges, what we mean is that as we look at each individual term and we go through them sequentially, they are approaching some number, right? They're getting closer and closer to some number that we would call the limit. If they don't, then they diverge. If they're getting unbelievably large or unbelievably large in the negative direction, then we write the limit is equal to infinity, but really we mean it diverges. It doesn't converge to a number. Otherwise, if it does get closer and closer to some number, then we say that it converges. So we're just looking at the actual terms of the sequence, okay? When we talk about a series, right, we are now taking those terms and adding them up. Right? So now convergence means something different here. They might be getting closer and closer to some number. For instance, maybe I'm doing the series, the simple series, each term is the same. They're certainly all getting closer and closer to one. They're actually just at one. And so we would definitely say that the terms converge. If this was a sequence where every single value was just one, it converges to one. But as a series, adding them up, continually adding one just grows and grows and grows and grows and grows. So we need a different notion of convergence here. And what we do for convergence here is we look at the limit as n goes to infinity of what we call the partial sums, right? So what that means, I'll use the notation that might be a little bit difficult to look at, but let's write it this way. I equals 1 to n of a sub I. So what we're doing, what all this notation is saying is, if I write down the first partial sum, that's just the first term. The second partial sum is the first term plus the second term. The third partial sum is the first term plus the second term plus the third term, and on and on and on. Let's go up to the nth partial sum, will be the sum of the first n terms, right? If these numbers are somehow just getting closer and closer and closer to something, then we say the series converges, right? So if we're adding, let's say, 1/2 plus 1/4 plus 1/8 plus 1/16, right? Those partial sums, let's write this out. If my series was, let's say my series was 1/2 plus 1/4 plus 1/8, plus 1/16, and on and on and on. If I look at the partial sums, it's going to be 1/2. 1/2 plus 1/4 is 3/4. S2 is 1/2 plus 1/4 plus 1/8 is 7/8. And so on. If you do a little bit of algebra or just kind of notice the pattern, you can prove to yourself that the nth term is going to be, let's see, 2 to the n. Oops, this is the third. That's throwing me off. 2 to the n minus 1 over 2 to the n. Right? So 2 to the n, like we have 8 in the denominator, 4 here, 2 here, 2 to the 1, 2 squared, 2 cubed, and the numerator is just always 1 less than it, that this limit approaches 1. So this, we've created a new sequence from our series, the sequence of partial sums, and on and on and on, right? And so then we do convergence of this sequence, referring back to the same kind of sequence, convergence of sequence that we had over there, right? So convergence of a series is determined by the convergence of the sequence of partial sums. So they're related issues, but they're not exactly the same. And that's why you can have cases where a sequence converges, but the series made from that sequence doesn't converge. I gave you a simple example up there of 1 plus 1 plus 1 plus 1. Okay, that was kind of the first big idea, right? Then we started looking more closely at convergence of these series, right? Writing out the partial sums is not always convenient. We've done a few examples of this, but it's not typically how we're going to do things, right? They're good for learning and getting a little bit of an understanding of what these sequences are, or what these partial sums are, but there are some better things that we can do, that what we call our convergence tests. A habit of oops, my setup's a little wonky, so I feel like I'm being sloppy. Let's nicen this up a little bit. Let's make a nice straight line. That's better. And then, all right, so now we want convergence tests. So we have a whole bunch of convergence tests. Right, and I think I'm just going to write them out. It'll be nice to see them all in the same place. So we've got the test for divergence. We've got the geometric series, right? So it's not strictly a test, but if we recognize, I guess you could call it a test, recognize that it's a geoseries, and then we know things about its convergence. We've got the integral test. We've got p-series test. We've got the comparison test and the limit comparison test. What else? Alternating series, absolute convergence. We've got the root and the ratio test. I think that's all of them. Okay, so I'm not going to go through the details of each of these tests. I have individual videos, examples with all of these, and some notes on them. But I just want to make a comment because in many conversations, people with students, I've had similar kinds of ideas that even when applying these tests, they don't feel like they've done the math. It's very uncertain if you're doing what you're supposed to do. And there's a good reason for this. Using these tests follows a pattern that we're not very used to using in our mathematics classes. You know, the beginning of mathematics is all computation. What are our times tables, adding things up, whatever it is. You're doing a bunch of computations. At the end, you get a number, right? And then we start to get into like things like derivatives and integrals, where you might get a function as an answer, but you still kind of end your problem with a bunch of, you know, multiplication, algebra and stuff equals a thing, a number, a function, whatever it is, right? We're now in a case where our answer is like a collection of sentences. The whole thing is the answer. There might be some computations in there, like a limit of some sort, but the way these problems are structured when we're testing for convergence, right? All of these tests follow the same pattern, right? Each one of these tests has some conditions. That's not how conditions are spelled. And actually, let's try conditions and a result. For instance, the test for divergence. The condition is if the limit of the terms of a series is not 0, right? There's your conditions. Then the result is we know that series does not converge. In other words, it diverges, right? So the process for these problems is to show that the conditions are true, and then we get to claim result. Right? That looks like an H, but that's the word result. So just a really quick example, if I have something like this series, I can use the test, and I want to know if it converges. A quick, right? There are many ways to do this limit, but this limit is 1. So now I've shown that the limit of the terms of the series do not equal 0, right? If I want to be really clear, I can remind everybody that 1 is not 0. And because I've shown that the conditions are true, therefore, the series diverges. So the conditions of the test for divergence are met. The terms do not go to 0. So I get to claim the result. The series does not the series diverges. I might say something like, by test for convergence, or test for divergence, different texts call it different things. It's really a test for divergence, I guess, because you can't prove that anything converges with it, but you can prove that things diverge with it. So that's the structure of this problem, right? The only computation is up here, but what I'm really doing is showing you that the conditions are met. Okay, so let's do a couple more examples to hammer this point home a little bit. I'll do them in a little more detail, I think. Oh, sorry, I want to do one other thing. This was an easy example. I knew that I made it so that the test for divergence would work. One of the tricky parts is you might say, oh, I want to use the test for divergence, and you try to use it, you get a limit of 0. Well, that doesn't tell us anything. It only doesn't tell us that it diverges. In other words, if a series has a limit, if the limit of the terms of a series is 0, the series may diverge or it may converge. So we don't know anything. We're where we started, except not exactly where we started. We've eliminated something, one of our tests. The test for divergence didn't work. We move on to the next one. This is another part of this which is difficult. You might try something and it just doesn't work. It's not because you got something wrong. It's because that particular test didn't work in this case, right? If you have a collection of presents and they're all wrapped up and you're wondering what you got, and you're a little kid waiting for your birthday, you might pick up a box and shake it, right? And if the gift in there is a tambourine, shaking it might be the test that lets you know what's in there. Great, it worked. You now know that's a tambourine. But if what's in your box is a pair of slippers, shaking it probably wouldn't tell you that. You hear something moving around, you don't know enough, you don't know anything. It's not that shaking it isn't a valid attempt. It just didn't work in that case, and you'd have to try something different to figure out what's inside. And that's what we do here. We're going to try a few things until we find one that works. And in many cases, there's more than one that will work too, and we'll do an example of that. All right, so let's investigate the convergence of the following series. There was a similar one on one of the assignments. This one's just barely different, and it will have but it'll take a very different half because of that. So we've got the series as n goes from 1 to infinity of the natural log of n over n squared. So let's go through as if, I've solved this already, but I'm not going to jump to the answer. I'm going to go through the process. The first thing I might try, especially if I haven't seen one like this before, is the test for divergence. Which means I'm going to take the limit, then goes to infinity. Since the numerator and the denominator both go to infinity, I'm going to use L'Hopital's rule. Take derivatives of each of them individually, and I get, what is this, 1 over 2n squared equals 0. I get a limit of 0. So the terms are getting smaller and smaller and smaller until they nearly vanish, right? They're getting incredibly as close as we want to 0 by taking n large enough. However, some things that do that converge and some things that do that diverge. So the test for divergence was inconclusive. So we might move on to something else. Let's try a comparison test. Okay. So in a comparison test, right, there's different ways to write this. So we could say something like this. Suppose we have positive, two positive sequences where one of the sequences is always smaller than the other. And the series of the larger sequence converges, then the series of the smaller terms converges, right? So here are our conditions. We have to have two series, one that's smaller than another, two sequences, one that's smaller than another, and we know that the series built out of the bigger sequence converges. Then here's our result. We know that the series built from the smaller sequence must converge, right? It's a little bit like the squeeze theorem. Kind of feels a little bit that way, right? It just has nowhere else to go if that one converges and it's pinned between that one and 0. Okay, so what do we have? We have a sequence that we want to know about. That's the A sub n. I need to find a sequence to compare it to, and I want two things to be true. I want the sequence I'm comparing it to be larger for all terms, and I want to know that it converges. Right? So here's my original sequence. Ooh, I need my ln of n. I could compare it to something like n over n squared, right? This is certainly smaller. The reason we get that it's smaller is if you consider the graphs of the natural log and x. So this is the function y equals x. This is y equals natural log of x. X is always larger than natural log, so this thing is going to be larger. So we found a sequence that it's under, but this thing is equal to 1 over n. And it turns out that this series doesn't converge. It diverges, and we write equals infinity to mean it just keeps growing, okay? So this satisfied one of the conditions, this first condition, but it didn't converge, so I can't really use it, right? Now, there might be another series we could compare to that will work. I don't know an easy one to show to satisfy. This was the easiest one to satisfy the first condition. So I'm going to call this, I'm gonna move on, right? It might turn out that none of the other tests will work, and I'll have to come back to the comparison test and think a little bit harder. But I prefer to kind of jump at a couple quick ones, see if something easy shows up. And if it does, go with it. If it doesn't, move on. If I get through all the tests and nothing's worked, I'll come back and try a bit harder. Okay, let's try a limit comparison. Okay, because now I don't need to have this condition that they have this size comparison, right? So now I have a limit comparison. What I need, it's something like if two series and the limit as n goes to infinity of a sub n over b sub n is equal to a finite number, then both series converge or both series diverge, right? So if they have this limit, if they have this finite limit, sorry, I hit the button and I jumped screens. Okay, sorry, I'm back to where I was. If the quotient of the terms of these two series have a finite limit, then their convergences are locked together. They both do the same thing, converge or diverge. This gives us a little more freedom in choosing the series we compare to. So again, how we use this, one of these series, I'll just say the series made of a sub n's is the series we're interested in. B sub n will be a series we choose for convenience, something whose convergence we know about, and so that the limit is, when constructed this way, is equal to a finite number. So let's try one. Let's take a look at, let's use the limit comparison. So we've got our series L sub n over n squared. This suggests maybe trying 1 over n squared. And we know this converges by the p-series test. Okay, it has a power greater than 1, right? That's the p-series. You have 1 over n to the p. If p is greater than 1, that series will converge. So let's try taking the limit of the quotient of these two. So we want to take the limit as n goes to infinity of the natural log of n over n squared, 1 over n squared. However, if we do the algebra here, this just becomes the natural log of n, which goes to infinity. Okay. So what happened here? Well, the problem is, not the problem, we chose a series and it doesn't have a finite limit to this quotient construction of their terms. That doesn't mean anything. We've learned nothing, but we didn't do anything wrong. And so this isn't really giving us any information, and we're still doing this process correct, right? When I have students and I'm grading their work, right? While if a student on an exam did these two things and ran out of time, they're getting some good credit, because it shows me that while they didn't quite get to the right test, they were doing the process correctly, trying some things and not being tricked by their results, not saying, oh, it's infinity, well, this must diverge. Nothing about this limit comparison test tells me that this diverges. It only tells me something if the limit is finite, right? That's our conditions. We have the conditions in this case are these positive series and a finite limit of the quotient of their terms. We didn't get that, okay? However, this gives me a little hint. Maybe I can try something similar and just change it a little bit so that I end up with a finite limit. Let me just do something off to the side here. The algebra I did in my head over there, we had natural log of n squared divided by 1 over n squared, which is the natural log of n over n squared times n squared over 1. And then these two canceled, and we were left with the natural log, which went off to infinity. Let's use the limit comparison on something a little different so that this n down here doesn't totally disappear. Because if I have n down here, right, some power of n, it will overpower the natural log of n. And that will give us a finite limit. So let's try this again. Let's now try the series n equals 1 to infinity of 1 over n to the 3/2. This converges by the p-series test. Again, power of n in the denominator, the power is greater than 1. We'll take the limit now. N goes to infinity. Same idea. I take the sequence of terms from the series I care about. I'm dividing by this new series that I just decided to try. This might have no result, but it's actually not too hard of an attempt. Let's see what happens. We get the natural log of n over n squared times n to the 3/2 over 1. Doing the algebra, this gives me natural log of n over n to the 1/2. Okay, now taking this limit, these both go to infinity. We get to use L'Hopital's rule. That's my little symbol just to let myself or a reader know what happens in this step. This becomes 1 over n. This becomes 1/2, 1 over n to the 1/2. If you work this out, all the little algebraic steps, we've got a 2, and it'll be 1 over n to the 1/2. This limit, the denominator grows, the fraction gets closer and closer to 0. This limit is 0. So now we have satisfied the first condition of our limit comparison test. We've satisfied both of them, pardon me. We've satisfied that they're positive series and they have a finite limit, right? We know, oh, I never wrote the rest of the limit comparison test. I forgot to write then the series both converge or both diverge. Sorry about that. So the conclusion is if they have a finite limit, then they both converge or they both diverge. Well, they have a finite limit. We already know that one of them converges by the p-series test. So therefore, the series, the natural log of n over n squared converges. Okay. All right. That was a lot. I know it's not necessarily obvious what you're supposed to do here. This is what we practice for. And this is also not the only way to do it, right? I had said sometimes I give up. If something doesn't work, I just move on to the next thing and don't work that hard. This one, I did this because it occurred to me I was close to having the limit comparison work, and just a slight adjustment made it work out for me. If you don't see that, move on to the next thing. I did this one as well with the integral test. You have to use integration by parts to get the antiderivative you need. You have to take limits of an infinite integral and all that stuff, but it works out into a nice, you get something finite and you satisfy the conditions of the integral test. So that's the other nice thing. They often have more than one route to success. Excuse me. So if you miss one, you might find another, right? There's no way to get better at this than to practice. And when we practice, we'll start to see little patterns and be able to jump quicker, right, to things that might work. So let me do one more example. Well, we'll probably do 2 more examples, but one more of this kind before I make a final comment. So let's look at this. This is, I used k, it doesn't really matter. 2 to the k over k factorial. Okay, so I'm not going to go through all the steps of trying a bunch of convergence tests for this, right? You could try the limit compare, or sorry, you could try the test for divergence, but this will go to 0. You know, go through a few of them, see what happens. Integral test isn't really good here. We don't know how to integrate factorials. Excuse me. This one, factorials, this is one of those patterns I've talked about factorials very often you can find convergence with things with factorials very often by using the root test. Often, I mean, it's kind of the only route. Factorials are difficult to deal with. Sorry, not the root test, the ratio test. The ratio test handles factorials very, very well. So I'm just going to do that one using the ratio test. In the ratio test, remember, we look at the limit, the absolute value of the quotient of successive terms, right? So you look at the n+1th term divided by the n+1 term, and you get some limit. And if this limit is, if this limit is less than 1, the series converges. If it's equal to 1, the test, let's just write this down. The test is inconclusive, meaning it didn't tell us anything. We move on to the next thing. And if it's greater than 1, including an infinite series, infinite limit, then it will diverge. So let's set this up in this case. So I'm going to write down the k+1 term. That would be 2 to the k+1 over k+1 factorial. The kth term, of course, is just as written. Then let's look at the quotient of these two. I'm doing this a little piece at a time instead of trying to do all this algebra at once. So I get 2 to the k+1 over k+1 factorial divided by 2 to the k, that doesn't look right, 2 to the k over k factorial, which is equal to 2 to the k+1 over k+1 factorial times k factorial over 2 to the k. We do some algebra. 2 to the k+1 divided by 2 to the k just leaves me 2, right? There's one more power of 2 in the numerator than the denominator. Right? What about k factorial over k+1 factorial, right? Well, you just have to remember what factorials are. Let's just do an example. If I have something like 5 factorial over 6 factorial, so like k over k+1 factorial, 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1. Notice everything's going to cancel except for that top term. That would be k+1. So this works out really nicely as 2 over k+1. Okay? And in fact, just can add the absolute value here since it doesn't change anything. Since k is positive, 2 is positive. This is just equal to 2 over k+1. Right? So this is how the root test or ratio test handles the factorials so well, they end up canceling in some manner like this very, very simply. So now we take our limit. Oops, that's a bar. We get the limit as k goes to infinity of, we just said this was all equal to 2 over k+1, which gives us a 0, which means this is a finite number, less than 1. This series converges. Okay. My instinct is always to say any questions because I'm used to talking to people, but sadly I am not. Just checking. All right, I've got time for one more thing. So the last thing I'm going to do in this, I want to say little video, but it's turning out to not be so little, is just look for towards the future. I'm going to go into a lot more I have gone into a lot more detail in some other videos. So this is just for the purpose of kind of putting this stuff in perspective. The reason we care so much about sequences and series right now, there are lots of reasons to care about them, but what we're really building for in this course is something we call the Taylor series. All I want you to know right now is that what we can do is we can represent a series by writing we can represent a function as an infinite series. And it will, when, not always, but for most of the functions we like, things like trig functions, exponentials, logarithms, that sort of stuff, we can do this. We'll go through those details I go through those details in other videos. But for our purposes, let's just say, generally speaking, the functions we care about, we can do this for, we can write them as a series that will have some coefficient. So C sub n is just a coefficient, meaning it's a constant that depends on n. It will change with each term, just like when we write A sub n is something that changes with each term. And it will have x minus some number to the power of n, right? We can write these, our functions, as infinite series, okay? For example, e to the x can be written as 1 over n factorial x to the n, right? Which looks like 1 plus x over, 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and on and on and on. Okay, so this is like the coefficient. The c sub n's are 1 over n factorial. I could think of x to the n as x minus 0 to the n, so that's the case where a equals 0. Okay, don't worry too much about this, and it might feel mystifying at first. We'll learn how to discover these, how to build these, and all that sort of stuff. But that's just where we're heading, right? And when we get there, what we're really going to care about is some of these series, these infinite series that represent functions, depending on the value of x, may or may not converge. So for example, here's a function represented by a series. Okay, so there's a function represented by a series. This is the coefficient is 1 over n. I just made it one fraction. X minus 3, that's the x minus a. So 3 is a in this one. A is 3 in this one to the nth power. We're going to test for convergence in the same way we have all along for these other series. We're going to use our convergence tests. This is another one that will work well with the ratio test. I'm not going to go through a bunch of mistries. You might try some other things, but I just want us to see where we're heading with this. So if I were to take the ratio test, I need to look at the quotient of 2 successive terms. Instead of dividing, I'm just going to multiply by the reciprocal. What do we end up getting? We have an n plus 1 powers of x minus 3 divided by n powers of x minus 3, leaves us with x minus 3 in the numerator. And then I've got n over n plus 1. So that's just algebra so far. I still do the same test for the ratio test. I take the absolute value of that quotient and take its limit as n goes to infinity. So that means looking at this. Now, x minus, well, let's do one piece of algebra with absolute values. I can split this apart into 2 absolute value quantities. X minus 3 doesn't change as n changes. We might put in different values of x, but changing n doesn't change those values of x. So as far as this constant, or as far as this limit is concerned, x minus 3 is a constant, and constants slip out front. We got n over n plus 1. Well, this is an easy enough limit to take. N over n plus 1 has a limit of 1. So our limit in the end is just x minus 3. Okay. Now remember what the ratio says. The ratio says, the ratio test tells us that a series converges if this limit is less than 1. So now we have to ask ourselves, when is this thing less than 1? So let's just write that down. We want x minus 3 to be less than 1. That's equivalent to saying x minus 3 is between 1 and negative 1. I can add 3 to both sides, so I get x is between 2 and 4. Okay, so it's still the same test. We're finding out the x values that make the condition that we want true, that this is less than 1. You can also find out what happens at the endpoints of this. I'm going to leave that alone for now. That's more detail than I want to go into in this one. Like I said, we cover this a lot more in other videos. But I just wanted us to see where we're going with these convergence tests. We're going to apply them to functions. And so what we find is that this series that I wrote here converges as long as x is between -1 and 1. We'd have to check what happens at the endpoints, or sorry, x is between 2 and 4. Well, we could check what happens at the endpoints, but we'll do that another time. I want to leave that here. Okay, this was long enough. I hope especially the beginning part gave us somewhat of an overview of this kind of big picture of, you know, all these little details we've been getting thrown at us. I know is a lot. And I guess the last thing I'll say is nothing's going to work better than practice to get us through this. Okay, that is it. Thanks, everybody. I will see you next time.